Then, as I announced, I start with the wild 410 for distribution in R10. Okay, and so one-step bracket generating nilpotent approximation. So along, I don't give the details. I just state the results. So in that case, as I explained, the bracket modulo delta mapping, you can projectivize, and it becomes a mapping from the Sub-Riemannian G24 to projective space on R6, and dimension of this guy is 4, dimension of this guy is 5. Then generically, you never meet, you are never, not only you are never convex, but in the direction, or in a certain direction, you do not meet the image of this mapping. Okay, nilpotent approximation along gamma in normal coordinates. As usual, it will be z dot, let me write it x now, x dot equals u, and then x is in R4. We have four controls, and so we have y dot equals x prime li u, and at the end w dot, the last one, equal x prime m u, li, and these quadratic form are in normal coordinate the components of the bracket modulo distribution mapping. Okay, and so all these guys are so in SO4, and as I explained also, we can already manage for we still have this constant chi. So these guys depend on W, of course. It is nilpotent approximation along the vertical axis, and I define, as usual, the chi of the, which is a function of W, of course, as the infimum over lambda of the norm of M plus lambda L norms, L2 norm. Okay. And I remind you that in the case of distribution of corank at most three, the interpolation entropy was given by the following formula: 1 over epsilon square, the sum dw over key w. Okay. When we were in convex, generically in the convex situation, it was like that. So this key still exists, and in fact, so it is very, since these guys, so we can manage already for this M be equal to this infimum, for lambda equal to 0. We can manage by a change of coordinates that doesn't change, by a change of normal coordinates that doesn't change the W axis. We can manage for lambda and this infimum is 0. And then what we know that since we are not convex, this M must have double eigenvalues. We know that because, as I explained, if you have simple eigenvalues at the minimum, you automatically are convex. Then this M has has double eigenvalues. How to manage with this double eigenvalues? It is very natural. SO4 can be split into the sum of quaternions plus the vector space of quaternions plus Q quaternions. So probably you know, but quaternions in SO4, they are is the vector space generated by the three matrices I, G, and K. I is just 0, minus 1, 1, 0, and minus 1, 0, 1. G is, so this is I. So G is, you have a block which is 0, a block which is minus 1, 1. And here, so since it has to be skew symmetric, it will be 1, minus 1. And, okay, you complete. And K is, so 0, block 0, minus 1, 1, block like that, and the opposite, then 1, minus 1 here, and 0 here. You have this IGK, you have, which is the basis of Q. These quaternions, they commute, sorry, they do not commute, they form the algebra, they are the pure quaternions. And you have this skew quaternions, you have I hat, G hat, and K hat, that I don't write, but you just change some sign. And quaternions and skew quaternions, they commute between them. A quaternion commutes with a skew quaternion. And moreover, the set of matrices that have double eigenvalues in SO4 is exactly the union of this Q, and the set of matrices with double eigenvalues is just equal to Q union Q hat. And these two spaces are orthogonal with respect to the usual Hilbert-Schmidt scalar product, natural Hilbert-Schmidt scalar product in the set of skew-symmetric matrices. Sorry.
Yes.
Okay. Thank you. Then you have this. And then the first thing that you then sorry, let me go into my notes. The first thing that you can do is to where is it? Sorry, just 1 minute, because my things are mixed. Where is it? Okay. I will probably write wrong things, but it is. It looks like this. I can't find exactly the good formula, but you have the. So you have y1 dot, y2 dot, y3 dot, y4 dot, and y5 dot, and of course w dot, the last one. You can manage the thing in such a way that it is this guy. Always. You know that it has double eigenvalues, then it is either a quaternion or a skew quaternion, and you can make changes of coordinates in changes of normal coordinates, which means changes in the surface that defines the normal coordinates. You can make changes for it like that, and at the end what we can prove is something like that. It is that almost y1 dot would be better if I can find the exact normal form, but apparently I mixed all my better if I can. Okay, I got it. So all of them. So this one will be high x prime, high plus rho w, high hat if I remember well. Sorry, high hat plus rho high u. Second matrix.
Жан-Поль, maybe take another flamaster. That near the blackboard is a good one.
Okay. So here you have high hat plus rho high. Second one is just G. Third one is just K. For 4 you can get G hat, of course. And 5 you get K hat. You can manage the things. And here of course you get the chi of W, which is the invariant in the convex case. Okay. Then now appears a new invariant rho of W, and moreover this absolute value of rho has to be smaller than 1. You can manage with this. And what does this rho do? It measures, it is new invariant, it measures distance to convexity. If absolute value of rho is equal to 1, you are in the convex case. And if absolute value of rho is 0, you are in the very simple situation. So absolute value of rho equals 1. So it turned out, but this is another story, that there is a paper by Roger Brockett on the we are in the free nilpotent situation, very old paper in the International Congress of Mathematicians a long time ago, in which he says things that are very close to this, that are partly false, because in particular he does not consider the possibility to be convex. This is wrong in his paper, but except this part of the paper is right. But these things have been, in completely other context, examined in this paper by Brockett. I don't remember the year of this paper. It was in the 80s, something like that. So you have this normal form, and you have a new invariant that measures distance to convexity, and what you can prove, so it is very long computation, but quite hard, but the structure of quaternions and skew quaternions helps a lot. You can compute explicitly everything. It is technical but easy, and what you get at the end is the following formula. It is this one I remember. This one I remember. It is the following formula. It is that the interpolation entropy as a function of epsilon is just 4 pi over epsilon square times the integral over gamma of 3 minus absolute value of rho of W over kw DW. I remind you that for the metric complexity we had 2 over epsilon square integral of dw over kw, and I remind you that in the cases of courant less or equal to 3, interpolation entropy as a function of epsilon is 2 pi times the metric complexity. Okay? Then if you look when absolute value is equal to rho, you get exactly this formula.
Epsilon square is in the last formula.
Sorry? If absolute value is equal...
No, in the right one, epsilon square.
Epsilon square, yes, of course. So, and when absolute value of rho is equal to 1, you, of course, recover the convex formula. So this rho, how do we proceed to do this? Well, okay, we get this normal form. At the end, it is not clear that this rho is invariant. But the only reason for which this rho, we conclude at the end that this rho is an invariant, since the key is an invariant, key can be. Okay? The only reason for which it is that it is a formula, it defines the formula for entropy, and entropy is intrinsic quantity. But I do not have any other interpretation or formula or intrinsic or any other intrinsic definition of this rho. At the end, once you have proved that this formula holds, then it becomes clear that this rho is invariant. No more than that.
Metric invariant. Metric invariant.
Metric invariant. Okay. And what about the optimal synthesis? So I remind you that in all other cases you had the first plane, the first eigenplane of this n, which is the minimum over lambda of m or lambda plus lambda L lambda. I remember that this, you have this, we have this chi which is equal to this, and when the minimum is equal to, so at the minimum, I call this matrix, at the minimum, this matrix is m plus lambda L, I call n, and I remind you that the optimal synthesis is like that. You turn, you have circles in the first eigen plane of L. Yes, then optimal trajectories are helices that project on circles that are in the first eigenplane of this matrix N. Now what you have on the pieces where you are convex, of course you have the same situation, and in the parts where you are non-convex, then you have components, so you split naturally in this normal form, you have the X space splits in x1, x2, x3, x4, okay, and these coordinates, and again you have circles, but here you have a circle with a certain period, which is 1, or okay, k1, and here you turn with a period which is k2 is twice k1. You have so optimal trajectories are again helices, but now you have 2 multiple periods. And so this is mostly the situation in this 410 case, but, and I will not say more, I will just say that this in fact completely generalizes to the one-step bracket generating situation, but partly it is less explicit. We have no clear expression of the interpolation entropy, but what is clear is that the optimal trajectories are, it is clear that the space of the X splits naturally into two spaces, and let me consider only the even case. In the odd case, of course, you have the zero eigenvalue of skew-symmetric matrices. It splits into two-dimensional spaces like that. Half you have if dimension of delta is 2n, you have n of these subspaces, and you turn in these subspaces. You don't know how many you have. You don't know how many you have. For some of them, you do nothing. You stay at the point. But at least for the first one, you turn with one period, and just after you turn with a double period, and just after third period. Then optimal synthesis is always like that. You have a certain number on a certain number of these subspaces. You have helices, and their period is successive multiples of the first one. It is what we can prove in general. So this was, up to this detail of convexity, proved in the paper of Brocket in the ICM, just in the free case. Okay. So this is, but we do not have clear estimates, as clear estimates of the entropy, but we have this construction. So result is like that. Look, it is in accordance with the generic case of corank smaller or equal than 3, where you have just a single period. That's it. Okay,
but
this is what we...
always multiple, 2, 3, all integer multiples.
And successive integer multiples, but maybe not all. Not all. But in free case, of course, generically all, except at isolated points. Well, no, even generically successive, because generically you do not cross the
even in not free case, it is still.
It is even in non-free case, it is still successive multiples, but not all. It stops at some time, and you can see typical example of non-free case is corank 3. Corank 2, Corank 1, Corank 3 case, in which you have just one. Okay, so it is finished for one step. What I want to do now is, in the remaining of my time, is to explain quickly the case. So now I focus on rank 2 distribution. We know already a lot about that. We know the case 2, 3, we know the case 2, 3, 4, and we know the case 2, 3, 5. In this 2, 3, of course, we have this picture, it is one step. In 2, 3, 4, 2, 3, 5, you have the Euler periodic elastic downstairs. Okay, so now I want to study situation 2, 3, 5, 6, which is a priori generic situation. It is generic in the sense that all brackets appear that have to appear natural. So nilpotent 2, 3, 5, 6 case. So I go to this, and it is, as I said, it is the case of the ball with a trailer. I remind you, you have the equation of the frame attached to the ball is like that, where omega is 0, 0, U1, U2, 0, 0, U2, minus U1, minus U2, 0. This is the omega. This is the motion of the frame attached to the ball. You have the motion of the contact point. So what is the state? The state is on the plane is contact point xy of the coordinates of the contact point, frame attached to the ball, and since you have a trailer attached to the ball, you have one angle more. It is the angle of the axis to the center of the ball with, say, the vertical coordinate. And then you have some xy equals u1, y1 equals u2, and you have one angle, the angle of the trailer, and you have something like that, 1 over L, where L is the length of the bar, times cosine theta u1, plus or minus, I don't remember, maybe plus sine theta u2, something like that. So these are the equations. For the nilpotent approximation along gamma, we have there is the following normal form. Of course, it will be. We are in for a distribution in dimension 2. Then it is very useful to consider the normal form that I gave in normal coordinates that are valid whatever the. You know one thing that I explained. So you have x dot 1 equals u1, x dot 2 equals u2, and starting from this, so y dot you have always x2 u1 minus x1 u2. That factors out. It factors out something. Exactly. Not even for the nilpotent approximation. This is true in normal coordinates. Factors out times something. This something now without changing the fact that coordinates are normal and without changing the vertical curve always, this you can put to 1. And after that, this is just a bracket, okay? And y is just first bracket modulo distribution, no more than that. Y dot, sorry. And after that, you have z1 dot and z2 dot in this nilpotent approximation. That also they have to be the same. x2 u1 minus x1 u2 always factors out. x2 u1 minus x1 u2, but in the nilpotent approximation you must have a term of it must be of higher order, then and you can manage by changes of normal coordinate to put x1 and x2, and at the end it remains w dot that has to be the same, x2 u1 minus x1 u2, but times a term of order 2. What is a term of order 2 here? It can be a quadratic form in x, q of x. That will depend on w, of course, because I am considering nilpotent approximation along gamma, plus maybe a term in y, but this term you can, by a change of the form w tilde equals again w minus, I don't know, something like that, y squared over 2, a change like that cancels the w, and this chain doesn't change the fact that the curve gamma is the same, because on gamma y is equal to 0, okay? Then here you just have a quadratic form. Here you just have a quadratic form. Okay, so normal form is like that. Now, what is invariant in this QW? This QW, you can define it in the following way. You take F1. Okay, I prefer, you write the system under this form. FU1 plus G U2. Fg is orthonormal frame. It's here. You set H is the bracket, Fg. You say, now I shall bracket a lot, then my convention is that I bracket from the left. I bracket from the left. So high will be FFG. G will be GFG. And do I need others? I need to generate delta 3. Okay. So, okay. Then, then I have 5 that are this, that generate delta 3. And I consider a one form omega that just annihilates delta 3. I consider a one form omega like that, that annihilates delta 3. Of course, it is not unite, it is defined by multiplication up to some function, but, and I consider, sorry, the following matrix that I shall write here. I consider the following matrix. It is the A of W, of course. It is d omega F1 I. Or equivalently, this is omega of the bracket of F1 I. It is equivalent d omega F2 I. They are. So these vectors are all in delta 3. And d omega F1G, d omega F2G. And due to the fact that you can replace by brackets, and due to Jacobi identity, this matrix is symmetric. You have symmetric matrix, and then this symmetric matrix has two real eigenvalues, lambda 1, lambda 2, and you can prove that the ratio R equals lambda 1 over lambda 2 is invariant of the problem. And so, of course, this matrix QW of X is just this one. So Q. In fact, it is this one. And you can prove that this ratio of eigenvalues is invariant. Of course, the full eigenvalues are not invariant because you can multiply the form omega by anything, just the ratio. Okay. Okay. But so again, if you choose this form to be such that omega gamma dot equals 1, then now you get invariant not only of the Sub-Riemannian metric but of the motion planning problem, and in that case you have lambda 1 and lambda 2 become invariant. And so what happens for the ball with the trailer? There is a miracle in the ball with the trailer. This matrix, this symmetric matrix, is in fact a multiple of identity, x1 square plus x2 square. It is multiple of identity. The ratio R is equal to 1. Case R is equal to 1. as I explained yesterday, if I want to move as far away as possible in the direction of W, I have just, it is necessary that it is geodesic of the metric. So what I want to compute is geodesics of the metric that have given lengths and such that so geodesics of the metric that meet the W axis. It's the only thing that I have to compute. It turns out that the Hamiltonian system attached to the metric is integrable if in the case r equals 1. This is miracle. I cannot prove it, of course, because it is always very difficult to prove non-integrability, but I think that for r different from 1, it is non-integrable. At least it is integrable in the case r equals 1, and I show you how. I would like to keep the last part of my lecture after the poll for the Darboux case. So how much time do I have now to finish this first part?
3 minutes.
3 minutes? Oh, well. Okay. So maybe 5 if you allow me. Okay, then. Why? So you want to integrate this guy. So what you want to integrate, you have the Hamiltonian, which is as usual 1/2 pf square plus pg square. You said since level, you choose level 1/2 to be parameterized by arc length, and you set pf equals cosine phi as yesterday, pg equals sine phi, and you get that phi double dot is equal to minus p ffg plus cosine phi minus p gfg sine phi. You call this guy lambda. You call this guy mu, and you compute lambda dot and mu dot. So lambda dot is equal to p ffg cosine phi plus, including the minus, okay, plus p g gfg sine phi. Okay, and now you have to do it once more. These guys, you compute, these guys you compute, and in fact if you compute in the normal form, you get that, so you have, and for mu dot you have similar expression. But if you compute in the normal form, you have that gffg is 0, and fffg is also 0. So, lambda dot in fact is equal to this, because this one is 0, and mu dot is equal to p ggfg sine cosine phi. It is converse, sine phi, cosine phi. But this guy, if you compute, if you take a normal coordinates of the adjoint vector being p1 to p6, if you compute this guy, it's just p6. It is just p6, and then what you get? You get the following. Once you have computed this, so there is another point. As you could see, the Hamiltonian does not depend on certain variables. It does not depend on the two last variables, W and it does not depend on the last variables. Then you have, it does not depend, of course, on the variables y, z1, z2, the Hamiltonian. Then you conclude, in fact, no, P3, the Hamiltonian does not depend. Then you have P3 equals 0, P4 equals 0, and sorry, P3, no, but it does not depend also on W. Then P3 to P6, sorry, are not 0, but constant. You have this more. P3 to P6 are constant. Okay? And due to this, you have the following fact, that lambda is equal to 3 over 2 P5 plus P6 x1. And you have that mu is equal also to 3 over 2 P4 plus P6 x2. Once you have this, it is almost finished. What you get at the end, you get phi double dot equals, you get phi double dot, which equals to minus P to equals to minus mu sine phi, but sine phi is just so minus mu sine phi, but sine phi is just sine phi is just x dot, because it is it's just y dot or x dot, maybe x dot or y dot. Then this gives you that phi prime is equal to x plus a constant. And then summarizing this, you get the following result. I have to explain it because it is interesting. Once you have done this thing, you get the following. x1 dot equals sine phi, say. x2 dot equals cosine phi. I change them, in fact. Phi dot equals a certain constant plus 1 over 2p6 lambda square plus mu square, you get that. And you get that lambda dot is equal to p6 sine phi. And you get that mu dot is equal to p6 cosine phi. But this p6, if you just renormalize the length, you can choose to be 1. You will not compute the length, given length, just the length that you required will be multiplied by some constant. So this P6 you can force to be 1. Then you have this set of equations. This is the equation of a curve on the plane lambda mu, the curvature of which is a function of the distance to the origin, quadratic function. I have to stop, it is a pity, because the most interesting come now. So you can integrate, and what you get is this hyperelliptic picture, but the end of this integration story is very interesting, and will help me to explain why I think at the end that the conjecture is false. But nevertheless, so you do the job, and you find, so it turns out that this, okay, you find, I cannot give details, so you find this three loops picture, which is a hyperelliptic curve, which is projection down of the optimal interpolation entropy trajectories. Okay, thank you. Sorry.